Hello everyone, welcome to DFT Deep Dive.
In this video, we will break down a complete DFT cycle. First, we'll look at fundamentals, why chip needs DFT, how the transistor explosion changed everything. We will travel back to see what testing in the early days looked like. We'll clarify a major point of confusion what DFT versus verification is and why defects are unavoidable. We'll see what controllability and observability is and how we use AT to check our design. We will track where testing lands in the chip design cycle. We'll see the business side of thing, what is yield, and why early detection matters. We'll walk through the physical silicon test cycle from wafer to chip. We'll address the limitation of test coverage. I'll share my top references so you can keep learning. Let's start. We will address the basic question why your chip needs DFT. Imagine a scenario where rocket is ready to launch. It has thousands of parts working together. Engines, wires, control systems, sensors, computers. But even if everything else works perfectly, one small faulty sensor can keep the entire machine at risk. A modern chip is just as complex. It has billions of transistors working together. If one critical transistor fails, it may malfunctions the entire chip. So, how engineer test this so small, so complex, so densely packed chip? The answer is DFT. Without DFT, testing a modern chip would be nearly impossible. So, let's dive into this fascinating world of testing and understand how DFT ensures that the electronics we use every day actually works. Let's take a look at the transistor explosion. To understand why modern testing is so different, we have to look at how rapidly the hardware itself evolved. In 1960s, we had a few dozen transistors in a chip. In 1986, the first megabit random access memory which had 1 million transistor came. And in 1994, the microprocessor had a 3 million transistors. But today's technology, we have a billions of transistors in a single chip. What led this explosion? Shrinking transistor sizes. Smaller transistor meant we could squeeze millions and eventually a billions of them into the same exact footprint. Example, if we can put thousands of transistors in this chip, now we can put billions of transistors in the same exact footprint. So it made testing modern chips dramatically more complex.
To understand and appreciate why we test the chips the way we do using design for testability techniques in the modern chip, we need to look at how testing used to happen in traditional design. Let's take an example. Consider there's a chip which has an AND gate and A and B are the primary input of the chips. Let's assume A is 1, B is 1. What is the expected output here? It is 1. But the actual output we got from the chip is 0. So there is a mismatch between the expected and actual output. So this chip is a faulty chip. This is one combination we have checked. What are the other combination we need to check in this chip? 0 0 0 1 1 0. When it is 0 0, we need it to be expected output is 0. Here also it is 0. When it is 1 0, the expected output is also 0. So here we have covered 100% of the design in the sense the all the input combinations. If we have only two pins, the total input combination is 2 power 2, which is 4. Let's assume we have a 5 pins in the design. So 2 power 5, we have 32 input combinations. When we can cover all the scenario in a design, it means we have covered the 100% of the design. So we will check all these 32 cases and see whether the design is passing all these cases. In traditional designs, the number of input pins are not much, they are comparatively less. But in the today's chip technology, we have over 1,000 primary input pins in a design. Do the math. 2 power 1000 is such a big number. It is, the total number of atoms in the entire universe is that much number, this 2 power 1000 comes. So if you try to test a modern chip the old way, checking every input combination one by one, it would take longer than the our lifetime. So this massive combinational explosion is exactly why traditional testing has died. This is why design for testability became mandatory for the modern chip design. Wait a second. What I just explained sounds a lot like what design verification does, right? So, how is DFT different from verification? Let's use the same AND gate example. Suppose we have two inputs of AND gates as 1 and we expect the output to be 1, but instead the output is 0. So, there is a mismatch here. In design verification, this indicates that the design is not behaving according to the specification. In the spec, we are telling if we provide two input of the gate as 1, it needs to give an output as 1. That's what AND gate behaves like. But if it doesn't obey, then we call there is an RTL bug or a design error. Verification engineers use simulation to find and fix these issues before the chip is sent to fabrication. This is a pre-silicon verification, where the design is still in the RTL stage, where before the silicon is actually manufactured, this verification we do. Now let's look at the same situation from a DFT or testing point of view. After the chip is manufactured, we apply test pattern through the ATE, that is automatic test equipment. If the manufactured chip responds correctly to these patterns, it gives us a confidence that the silicon does not contain any physical manufacture defects. This is a post-silicon testing. So this is happens on the real silicon, and whatever the defects we get is through the manufacturing process these defects we are getting. So then obviously with this explanation you need to understand why we need both verification and DFT, because design can be functionally correct and pass 100% of simulation tests. It still fails after manufacturing due to physical defects such as open, shorts, or process related issues. But verification will never see these defects because they don't exist in the RTL or simulation stage. They are introduced during the manufacturing process. So the verification peoples ask the question that did we design it rightly? And the correct question for this is, was this chip built correctly? We still need testing after manufacturing because defects are unavoidable. Let's understand why. The scale problem. A modern chip can contain around 10 to 50 billion transistors, all packed into a tiny die that may be almost the size of a fingernail. And today the feature sizes are in range of just a few nanometer. That is extremely small. At this scale, manufacturing has to be incredibly precise. Even a very tiny imperfection during fabrication can create a physical defect on the chip. Why defects cannot be completely eliminated? Even though semiconductor manufacturing happens in highly controlled clean rooms, it is still impossible to make the process 100% perfect. For example, a tiny dust particle can land on the wafer and accidentally short two metal wires. During photolithography, the light exposure may not be perfectly uniform across the entire wafer. Also, during heating and cooling steps, different layers of the chip expands and contract, which can create stress or small physical changes. So, even with advanced manufacturing technology, defects can still happen. That is why chip yield can never be 100%. So, What this defect leads to? A defect is actually a physical problem on silicon, but the fault is the logical behavior caused by the physical defect. Let's take the same example of AND gate. This is input A, there's input B, and let's assume there's a stuck at 0 for one input of the AND gate. And if we provide 1 as an input, we we simulate here 0 because this wire is always stuck to 0. Irrespective of whatever the other input is, it will always be 0. So the expected was 1. There is a mismatch. This leads to the functional failure of the design. This is where the physical defects change to logical fault and then the functional failure. That's exactly why DFT is needed. DFT helps us convert these invisible defects into detectable logical failure using test patterns. Let's understand how controllability and observability in DFT helps us to find faults on the design. DFT is mainly about making internal nodes easier to control and observe. Let's take an example which has an AND and OR gate in a design. The primary inputs are A, B, C and primary output is Y. These primary inputs and outputs have direct controllability and observability on them. But the internal nodes won't be having. Let's take an internal node X here. To have a controllability of 1 on it, I have to make A and B as 1. And to get the observability of this X in Y, I have to make C as 0. Why I need to make C as 0? Think think of it like this way. If you make C as 1, what will happen? We don't know whether the 1 value is coming from X or C. So to make sure the observability of X is what I want to get, I have to keep non-controlling value for an OR gate, that is C for the other input as 0. So how this controllability and observability helps me to find a fault? Let's take an example. Let's take stuck at 0 as an example. If this wire is stuck to 0, what will happen? The output will change to 0 because 0, 0, 0. So the expected value was 1 and there is a mismatch here. So that's how we can differentiate the good chip versus bad chip. This helps us to differentiate what is the good chip expected value and whether it is producing the output the way we wanted. That's how test controllability and observability in a DFT helps us to find a faults in the design. Let me explain how testing is performed using an automatic test equipment. There are two major steps here, test generation and test application. During test generation, engineer creates a set of test pattern designed to exercise different functionality of the chip. Along with these patterns, the expected output are also generated and stored within the ATE system. And in test application, once the test patterns are ready, the ATE applies these input stimuli to the circuit under test. As shown in the diagram, the input test stimuli is sent from the ATE to the circuit under test, and the circuit processes these inputs and produces an actual output response. Simultaneously, the ATE already knows the expected response should be for each test patterns. In the output response analysis, the ATE then compares expected response with the actual response. If you see here the stimulus, the input stimulus we are giving, and this circuit will produce the actual response, and there is a comparison unit where it will take the actual response and the golden response, that is already we know what is the expected response. Both it will compare. If both matches, then it is pass. If there is a mismatch, then this circuit fails. And you can see image in the right side where typical ATE machine used in semiconductor manufacturing and even in validation labs also. This equipment automatically generates signals, capture responses, perform comparisons, and record test results at very high speed, enabling efficient testing of large volume of devices. So where does testing fit into the chip design cycle? The real question is, where doesn't it fit? It all starts with the design specification, where we define what the chips needs to do. Engineers then create the design, but before moving forward, we ask, does it actually work as intended? That's where the design verification comes in. Next, we had design for testability features, making the chip easier to test later. Once these features are inserted, we validate them to ensure they are ready for manufacturing. Now comes an important step, pattern generation. Think of this pattern as a set of carefully designed questions that we will later ask every chip. Before using them, we validate the pattern through gate level simulation to make sure they will catch defects accurately. After fabrication, the real chip is here. We first perform wafer testing to identify fault in a die early. The good chip are then packaged and move on to package testing and final testing where we check functionality, performance, and reliability. Finally, all results come together in quality assurance, ensuring that only chips meeting the highest standards reach customers. Now that we have seen how testing is integrated throughout the chip design cycle, let's talk about why it's so important to test as early as possible. Imagine finding a defect during wafer testing. At that stage, fixing or filtering out a bad chip costs only a few cents. But if that same defect escapes to the next stage after packaging, the cost increases significantly. As the chip moves from the wafer level to package level to board level to the system level, the cost of detecting and addressing a defect grows many times, often by about 10 times at each stage. Looking at a chart, a defect that cost around $0.01 to identify at the wafer stage may cost $0.1 at package test and $1 in board level and around $10 at system level and potentially over 100 once the product reaches the field and for customers. At that point, we are not just dealing with the faulty chip. We may face product return, warranty, cost, service efforts, customer dissatisfaction, and even brand reputation impacts. This is why the semiconductor industry invests heavily in DFT, pattern generation, verification, and comprehensive testing. So, finding a bug early is cheaper. Finding it after the product ships can be extremely expensive. Let's understand what is yield. Yield is one of the most important metrics in semiconductor manufacturing. Simply put, yield tells us what percentage of the manufactured chips are actually good and can be sold. As shown here, yield is calculated as a number of good chips by total chips manufactured. For example, if we manufacture 1000 chips and 950 pass all tests, the yield is 95%. Naturally, higher yield means more sellable products, lower manufacturing cost per chip, and higher profits. So, what causes yield loss? There are two major reasons. One is catastrophic defects. These are random physical defects such as shorts, opens, or manufacturing imperfection that can make a chip completely unusable. Second one is parametric defects. They are manufacturing variation that don't completely break a circuit but causes it to operate outside its specified limits. Like the device would be too slow, too much power consumption, or wrong voltage threshold. Here the chip works but not well enough. It fails specs, not functionally. Let's understand what poor test cases are. The first is a test escape. Where a bad chip passes testing and reaches the customer, this can lead to field failures, returns, and reputation damage. The second one is overkill, where a perfectly good chip is incorrectly rejected during testing. In that case, we are throwing away a product that could have been sold. So, effective testing is really about finding the right balance, catching defective chips while preserving as many good chips as possible. So, if our goal is to find all defects, why can't we simply achieve 100% testing? Let's look at the challenges. Huge design size. Modern SoCs contains billions of transistors, which means there can be an enormous number of potential fault locations. In practice, it is impossible to generate tests that detects every conceivable fault within reasonable time and cost. As the design grows, achieving complete fault coverage becomes increasingly difficult. Second is limited controllability and observability. Now, even if we want to test a specific internal node, can we always reach it or observe its response? Not really. Many internal signals are not directly accessible from the chip pins, making complete testing difficult. Next come high test time. What happens if we keep adding more test patterns? Coverage improves, but testing time also increases. Since every chip needs to be tested, longer test time means higher manufacturing cost. The fourth challenge is large test data volume. So, this challenge of data, ATPG can generate millions of bits of test data. Storing and applying all that data requires additional memory and resources. So, achieving 100% testing isn't just limited by technology, we are also constrained by design complexity, accessibility, test time, and data volume. That's why the real goal is to maximize test coverage while keeping cost and test effort practical. Before we wrap up, I would like to acknowledge VLSI test principles and architectures designed for testability reference book as a valuable source for understanding DFT concepts in greater depth. Thank you for watching and happy learning.